Okay guys, sorry about that. It seems to be cutting out this morning, so what I'll do is I'll just record this video and you can watch it in your own time. So I want to really review some of the things that we looked at in the presentation yesterday about harmonic motion. A lot of information to take in there. So what I'm going to do is just go over the bits that you actually need to know and have a look at two specific examples of when we can apply harmonic motion. Now, the key principle for harmonic motion is that the acceleration of a system is proportional to the negative displacement. So if I have a simple pendulum like this, for example, then its acceleration at this point is going to be proportional to the displacement, i.e. at maximum displacement we're going to get maximum acceleration, but it's going to be in the opposite direction of the displacement, i.e. it's always going to be a restoring force. So acceleration is proportional to negative displacement. If you can look at any system and prove that acceleration is proportional to negative displacement, we can say it's oscillating with harmonic motion. Now, we want to get rid of the proportional sign, so the actual equation for it is acceleration is equal to minus omega squared displacement. Now, this term omega squared, or omega, is the angular velocity. If you imagine your harmonic oscillator being like a sine wave like this, you can actually describe that as a circle at different points. So, 90 degrees, 180 degrees, 270 degrees. So we can describe this point as, say, 0, 90, 180, 270, back to 360, or 0 again. So we can describe a harmonic oscillator as a circle. Only we're not going to use degrees in this, you're going to be using radians. Now, I can't think where you would need to put your calculator into radians mode because you're not using any trig functions or anything. And Mr. Cooper will deal with what a radian is if he hasn't done so already. But omega is measured in, or angular velocity is measured in radians per second. So it's how fast this thing will be turning around, how fast this thing is oscillating. So that's the constant that we will put in order to prove that it's oscillating harmonically. Now let's have a look briefly at three graphs. Should have room to draw them on here. I'll try and draw these accurately, though it is quite difficult. We take a sinusoidal oscillator. I'm going to do a displacement time graph for this one, and simple cosine wave looking something like that. If I were to differentiate this, you look at the rate of change, I would get velocity. The mathematicians amongst you would know this, and what you would get is a wave which would sort of be offset slightly. It would look, I don't know what's going on there. Try that again. A wave which would be offset slightly, so it would kind of follow something like that. And then if I was to differentiate again and look at acceleration, you would get something which would look like that. And what you notice is that at negative displacement here, a negative peak displacement, we've got maximum acceleration at that point. Now, as you go through this process, this is a bit of calculus, dy by dx. The equation for it, which we won't go over just yet, that comes up later, but you're differentiating using the chain rule in order to get the second derivative, acceleration, and that proves that acceleration is kind of the inverse of displacement. So acceleration is proportional to minus displacement. That is correct. That is what a harmonic oscillator is. Okay. Right. Obviously you can pause this and fast forward and look at it again, etc, etc. So what I'm going to do is take a look at two particular examples and prove that they are oscillating harmonically. I think the first one we'll do is a mass spring system. So we've got a mass on a spring, and we're going to displace it a certain amount, we'll call that x, and let it oscillate up and down. Now, going by Hooke's law, the tension, the restoring force, is simply be given by k delta x. Tension is a force, so F equals kx. That's just basic Hooke's law that he did in year 9. Now the restoring force is always going to be in the opposite direction. If I pull it down this way, the restoring force is going to try and push it back upwards. So we can say that the force is minus k delta x for this. Now using Newton's second law, F equals ma, I can rearrange that for acceleration. Acceleration is going to be F over m, and then if we can substitute in what the F is, that means that acceleration is going to be minus k delta L over m. Now going back to our important equation, the harmonic equation, acceleration is minus omega squared x. It's very similar to what you do when you're trying to make something fit the equation of a straight line, for example. I can substitute in the acceleration bit here. This delta L, sorry, it should be delta x, not delta L. This delta x is this x here, which means that omega squared, this one, must be equal to this one here, minus k over m. So that's kind of important. Omega itself, another way of writing this is 2 pi f. So 2 pi times the frequency of the oscillations. So that gives us an expression that 2 pi f squared equals k over m. Now, if I can rearrange all that, I get an expression for the frequency of the mass on a spring system. So F is 1 over 2 pi square root k over m. And that is our first important equation that we need to, well, you don't need to learn it, it's on the formula sheet, but you will be using it next lesson, so it is an important one. And I can see that up here, the acceleration, this k over m is the angular frequency squared, and displacement is there. It follows a harmonic oscillator, so we can say it's oscillating with harmonic motion. And interestingly, what it tells me is that the only two things that affect the frequency of a mass spring constant, mass spring system, is the spring constant and the mass. Nothing else affects it whatsoever. Okay, I'll move on to the second one, and then that will be it. So the second one is a simple pendulum, slightly harder. And these are the only two that you need to learn. You can do this for any harmonic oscillator if you work out the forces and what it's doing, but we only need to really know two. Let's take a simple pendulum, so mass on a string, and we've got, say, an equilibrium position down there, and it's oscillating at some angle, and at this angle it gives some displacement x there. Now let's have a look at a force diagram on these. This is a force diagram, not a not an actual diagram. We would have the tension coming up back this way, and we would have down here basically mg cos theta. The restoring force would be going back this way, and that would be mg sine theta, where theta would be the angle between the vertical. So the restoring force in this case for the harmonic oscillator we can say is minus mg sine theta. It's a minus sign because it's pulling it backwards towards the equilibrium position. So again, using F equals mass times acceleration. Let's plug in the acceleration part. So rearrange this for acceleration. It's just F over m, where the F is now going to be mg sine theta divided by m. Of course, the m's cancel out, so we end up with g sine theta. Okay, minus g sine theta should be really. But an interesting thing sort of happens here. At small angles, we can use something called a small angle approximation, and we can say that sine theta is actually equal to, if this is the length of the pendulum, and we've got x over there, it's actually equal to s over x. That's only true for small angles, and it's not quite true, it's approximately true. Which is why when we do this experiment, we only ask you to do very small angles, less than 5 degrees ideally. The bigger the angle you do, the less this approximation works. So we can use this rather than sine theta, and we can say A equals minus G S over X, or we can rearrange this, well, not rearrange it, we can change this slightly so that we've got minus G over X times S. Now that is a constant, and that equals omega squared. And then S is our displacement, A is our acceleration, and acceleration is proportional to minus displacement, so it works. So omega squared equals minus G over X. Again, we're going to use omega is 2 pi f. So if I write 2 pi f all squared equals minus G over X. Sorry, that's not X, is it? I've just realised I made a mistake. That should be L. I wasn't paying attention. S over L, that's this L up here. So change that. Hopefully you would have spotted that. But we're ending up with 2 pi f squared equals minus G over L. We can rearrange all that and we can get the final formula. I'll just write it up here, which is going to be the frequency is 1 over 2 pi square root G over L. And that is the second equation that we need for this. And again, that tells us that the only things that affect the frequency for a harmonic oscillator are G, the acceleration, and the length. The M makes no difference, it's cancelled out over here. And the displacement, if you're using small angles, doesn't make any difference either. The only thing that affects the frequency is the length of the bob and G. Okay, next lesson I'm going to give you some questions to try on this, so I'll post them out to you on Monday. Thank you.